So what this really gets down to, as far as improving the model beyond the Bohr model, is to understand what we're really going to fine tune is how we think about the distribution of the electrons. And so before we can do that, we need to reconsider how we think about the electron. And so remember in our earlier videos, we talked about how light has wave-particle duality. And so we consider a particle of light, we call that a photon. And depending on what kind of experiment we're looking at, we may see the light behave with wave properties or with particle properties. So this is also true for other types of particles that we consider mostly as particles, and this includes the electron. And so we introduced the concept of matter waves. Okay. And so this is described by the de Broglie equation, where the wavelength of the wave corresponding to some particle, okay, is described as the Planck's constant divided by the momentum. So if you remember from physics, right, that's how we define momentum. And so we can also write this equation as h over mv. And so this leads to a very famous equation. For instance, thinking about matter having wave-particle duality. Okay, so a particle also having wave behavior, and so this is probably something you will recognize, where we have E8 equals hc over lambda, which we've discussed in a previous video. If we then substitute lambda in here, what we get is equals cmv, right? And that leads to where c is the speed of light and velocity is also the velocity of the particle we're looking at. So that is actually still c, and so what you get is E equals mc squared, right? Which is the famous equation from Einstein. All right, and so what these relationships tell us is that, so again, what we're trying to get at is this concept of matter waves. So particles, right, matter with mass, such as electrons, can also have wave-like properties in addition to their particle properties. And so, for instance, let's say we had an electron with a kinetic energy of 10 electron volts. Okay? What this would correspond to when we calculate this out is a electron with kinetic energy of 10 electron volts. Okay? This corresponds to a wavelength for that particle of 0.3879 nanometers. Okay? And so this energy and this wavelength are consistent with an X-ray. A photon, an X-ray photon. And so, again, we typically think, we are used to thinking of electron as a particle, but it has some, it's going to have a wavelength, in this case, this 10 electron volt electron is going to have a wavelength of 0.3879 nanometers. And so, again, the important part here is that it has a wave property. And this is really important for something like X-ray diffraction, where we, for instance, can take a crystal of a compound and we can shoot electrons at high energy at the crystal, and we can get diffraction of these electrons and figure out back calculate the structure of the material that we have the crystal for, okay? And the data that we actually get from this is an X-ray diffraction pattern, such as the one seen on the board here, okay? And again, what we're seeing are dark spots followed by very light areas where there is no sort of indication that electrons are hitting anywhere, right? Again, this is similar to what we talked about when we talked about interference patterns, except, right, this is more two-dimensional in scope, where the dark places is where we saw detection of electrons, and the light parts are where we did not see detection of electrons. And so this results, again, because the wave-particle duality, we have wave properties which causes interference as these electrons are being diffracted off of atoms within the crystal structure. And what that's resulting in is a pattern such as this, where the dark areas are where there are points of constructive interference between the waves, the matter waves, whereas the light parts are where there was destructive interference between the matter waves. And again, we can use that information to back calculate the structure of compounds that are within that crystal.